Alright, there were quite a few questions with respect to how I build my cell packs, and as you can see it's my working area and my chargers are in the back. We're not going to talk about the MegaCellCharger and the MegaCell monitor. You've seen all the videos by now. We're in episode 6 or 7. So you've seen the batteries are being charged, discharged, we're measuring their capacity, we store them, we do the full drop test, etc, etc, and eventually you've got a box full of cells that are destined to go in your cell pack. And we run them to repacker. We selected all the necessary cells that you need for a particular pack, and then it's time to start building. Now you see a few different types. You see the ones with the bus bar on the top. You see a few experiments with the bus bars extended outwards and then interconnected with bolts. This one I don't like that much, but I'm currently also experimenting to find out what works for me the best. And I've been watching a lot of videos, and I'll put a few references to technical articles and some PhD studies about the cell design and yeah, things you should read if you have the time before you actually get into this. But for now we're going to build a pack which is somewhat similar to this one, except these are my test packs which I experimented with. They're also my junk cells, as you can see, all the different colors and stuff. And what we're doing now is I'm going to build one for my production environment, for my power wall, and initially I opted for a 14 by 14 cell pack, but it was just too large. It didn't fit my rack, and eventually I decided to go for a little bit smaller, a 12 by 11. So I need to scale this one down. Luckily those brackets are coming off quite easy. You need to do it carefully. They do tend to be at some points razor sharp. I do have a few cuts and bruises already with respect to these cell packs. So now we have 12, and we need to reduce this one to eventually 11. So we're 14, so we need to take out 3. And then we have a reduced cell pack size, which is fit for my rack, and also allows some space in the rack for the cabling and wiring and the thermocouples and stuff like that. We'll discuss that later on. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 7, 8, 9, 10, 11, 12. So that's one. Well, let's put this one aside, that will come in later. So once you've laid out your grid, and I'm really using these plastic holders because they have an added benefit. A lot of people are using salvage cells, and you see that the wrapping might not be 100% pristine. You might have a few tears and bruises on the outer rim. If you have, please rewrap them, because it's seriously a risk. But if there are very small ones you don't even notice, then adding them into a cell holder will make sure that the positive and the negative will never be able to touch. So that for me is one of the most important parts that I go for these things. They're a couple of cents per piece. If you buy them in bulk, they're even cheaper. And it allows you to add these cells really, really easy. And then later on, when we're actually going to mount the nickel strips, the nickel strips actually fit in the slots, allowing for very easy spot welding of the nickel strips onto the cells. And then, as you can see, I have 2 items protruding outside of the pack. There will be a copper rod inserted on the top. Then we fold them over, solder them, and eventually you have your cell pack. Now, I'm not going into the theoretical aspect for today, because that is a whole different topic which I will dedicate a separate episode to. But I can't stress this enough, is use your time wisely. You spend a lot of time in testing, peeling, sorting, and making sure that you selected the best cells, and eventually you will become you come at the point that you want to start building your pack for your inverter that you're going to use. Now that inverter has a certain wattage. Let's say if you have a 3000 watt inverter on a 48 volt battery pack, and then we're talking easily about 60 amps of current that your pack needs to be able to handle. Now when we're looking at those nickel strips, they are rated for 5 amps maximum, and the rating is across the strip itself. Now as we are having 12 in a row times 5 amps would mean that this pack would be able to take 60 amps in total. How do we come to that conclusion? 5 amps per strip, 12 strips, 5 times 12 is 60. Now of course there are also those crossbars, the horizontal ones, and they help in allowing you to draw a little bit more power. My recommendation is don't. Stay well below the maximum values. They do say 6 is the safe value for the nickel strips, which are 7 millimeters, 0.50 millimeters thick. And you could go up to 8, maybe 9, but then they start heating up, and the more warm they get and the more resistance you have, the worse it is for your cell. So don't do it. Now, having said that, so this pack is 60 amps. Now I've got already 3 or 4 packs in my rack, which means that the 60 amps that I need for my inverter, because it's a 3.3 kilowatt, will be divided over those 4 packs as well. And the capacity of the packs are almost the same, meaning that when I tie them into the bus bar, the total load is distributed across the 4, so it's 15 amps per pack, which is well below the specifications. Now I will be adding more inverters, up to 3, because I have a 3-phase system in my house, but that is something I think for a completely different video where I will show you my power wall. So let's get this one filled up. I will speed up the video and then we'll continue in the next step. Alright, so far so good. So I sized this one, and now the important part is that you are doing your orientation correctly. At some point you want to make sure that your pack is added into your rack, and if you take a good look, you see that this one is flush, this one is flush as well. This one has the protruding connectors, this one doesn't, and vice versa. So if you want to put them in a certain orientation, and let's say we take one which is already manufactured. So if you take this one and you want to set it upright, and you have one with the protruded elements on top and the other one not, it'll eventually come into an angle in your rack. So be careful that when you're constructing your cell packs, that you take a good look at your brackets and make sure that your orientation of the brackets are the same, so that the top and the bottom is flush. The sides, they might be different, that doesn't matter, as long as the way that you place them in your rack is flush, then at least they are not on an angle. So one thing that I learned as well myself. So the next step is, then we need to make sure that the batteries are oriented correctly. And what I do is I use a rubber mallet hammer, and slowly but steadily basically hammer these plastic holders into place, taking a good look that basically all the cells are almost centered to the holders. And then give them a slide tap, that will go in quite easy. Then once you've done the first round of slide tapping, you can tap them once more up until the point that the top of the cell is flush with the holder. So this one was the first round. As you can see, they're not quite there yet. So I will go row by row and make sure that they are nice and flush. So now everything is tight. We just take a good look if everything is nice and clean, no mistakes, all is looking fine before we actually go into the spot welding process. Now this looks good. There are a few places where it might need a slight tap, but overall this is looking fine. So let's progress. Now, I want to have my bus bar on the flat surface of the holders, not on the side where you have the protrusions and where you slide them in. I don't like that too much, so I take a good look at how my orientation is, and I make sure that the 11 cells are facing forward and the 12 cells are basically from left to right. Now I've already cut my nickel strip, so the only thing that I have to do now is actually place them onto the cells, take a good look if they are square, and if there's anything that might prevent the spot welding, and then we'll start and then we start to spot weld the cells. So let me make some space. Now what you can see is I'm using an electric spot welder. Actually a fantastic device. If you Google it on YouTube, you'll find quite a few reviews of them electric. And the benefit of the system is it allows you to use a 3S cell pack with 50C discharge rate to spot weld your cells. So it don't need to go onto the mains. It's a German manufactured device. When I assembled it, I fiddled a little bit with the timing settings, and actually in 5 or 10 minutes I was good to go. And this is my 4th cell pack now, excluding all the ones that I've used for testing, and hasn't failed at all. There are a few things you need to be aware of at some point. If you're not taking off the leads, it will go into a standby mode. You're thinking like, why is it not spot welding? You need to press the button once to resume spot welding. This is just to prevent you from getting stuck somewhere and it continuously starting to spot weld, and eventually you will have a hole in your cell and you don't want to. So that's protected. Also, if you don't use it for I think a few minutes, it goes into standby mode. You need to wake it up and then you can get going. One thing you need to be aware of, if you have it on your desk and the contacts are touching each other when you put in the XT90 connector, that's not recommended. It happened to me by accident, and I found that it started to spark. Luckily I was fast enough to take it out, but I don't know if it can damage the electronics. I certainly hope not, but it seems that it needs to start up first. Before you can actually touch the 2 electrodes onto the material Then the timer of 2 seconds kick in. I don't use the foot pedal, and it does a spot weld. Now what I do use is, I don't have a fan, but when you spot weld it will create fumes. So I'm using my my garage heater as a fan in normal occasions, basically sucking the fumes away from me, ensuring that I don't breathe in anything that might get vaporized by the spot weld. It is nickel. Well, nickel is not that healthy for you, especially in a gaseous form. If you breathe it in, you can have problems with your lungs. So be careful. Make sure that you do this in a very well ventilated environment. For now, for posterity's sake, I will do without, so you guys can actually see how I weld on one of the nickel strips, and then I put the video probably on pause, or I put my fan on. You might not be able to see everything that well, and then I continue with the spot welding. So, plugging this one in, you see the lights turn on, a few messages on the display. I set it to 12 milliseconds. I found that to be more than sufficient for the Samsung 29E cells and the nickel strip that I got from Encon. So the first step that I'm doing is I'm making sure that it is aligned center, and that everything is coming together. And I take one lead, press it down, making sure that the nickel strip is not moving, wait for 2 seconds, and then your first spot weld is on, and as you see it is tight. So that's okay. Then what I do is I guide the nickel strip all the way to the end and tack it once more. This makes sure that the whole strip will never move. Alright, so I will speed up this process. Basically I repeat the welding for the nickel strip, and we should be done in, what is it, 2 seconds per weld, 2 welds per cell. We have 22 cells in a row. So in principle, you should be done 2 times 2 is 4 times 24 in 96 seconds. So it's 1.5 minutes. It should be ready. Now let me reposition the camera, and then I hope that I can put my fan on and you guys are able to see what I'm actually doing. Because I really don't want to do this without any ventilation at all. So while we're working through the cell pack, there are a couple of things that you need to know. One of them is at least the recommendation is stay away from the center when you're spot welding. The reason for it is the cell internals of an 18650 are basically attached in the center of your negative contact. So when you put a spot weld over there, or if you're using your soldering iron and you go too hot, you might damage that particular part of the cell, and therefore, at least I'm staying away from the center when doing spot welding or soldering altogether. Now, I don't like to do soldering for the mere fact that when you do solder, the internals of the battery itself, the electrolytes, if they are heated to more than 60 degrees, the material already starts to degrade. Now 60 degrees with a soldering iron is actually nothing. Looking at a soldering iron, the solder itself will melt around 180 degrees, and if you set your soldering irons for, let's say, 320 and you're not using a big enough tip, the cell will actually draw out all the heat of your tip so fast that you keep your soldering iron on the cell longer than you actually should be doing. Also, you do have the tendency to solder in the middle. I don't know why. A lot of people just like to center things, but as already highlighted, the internals of the cell don't allow you to do soldering in the middle, or at least it's not recommended. The probability of you damaging the cell is just too high. So when you do solder, make sure that you're soldering on the sides, and make sure that you're using a big enough soldering tip, not necessarily the wattage. 100 watt soldering iron is more than enough, but make sure that your soldering tip is large. So it has a lot of heat already stored in the soldering tip, allowing the material under your soldering tip to heat up fast enough, so as little as possible heat is conducted in the cell itself. If you have your cell heated above 60 degrees, it will be degraded, and you don't want to have your just created cell pack broken before you've installed it into your power wall. And of course you want to use it for a very long time, so take those aspects into account. Don't overheat your battery above 60 degrees. It's really bad. One other thing, soldering the negative side of your battery is probably the worst to do. Soldering the tops is less risky. Reason for it is there are quite a few layers on the top of the cell, where you have your vent hole, of course, and your various layers, where you want to make sure that you're not able to overheat it that fast. Now the spark that you saw is me not paying enough attention, because if you don't push down the nickel strip onto the actual cell, it'll burn through your nickel strip and will not weld onto the cell. So be careful that when you're talking and working, that you pay attention to all your safety features. So what I do is I push down the nickel strip on one side and on the other side, and hold it down well firmly, not excessively. And especially because you're using reused cells, the probability of some remnants of the previous spot welds being still on your cell is very high. The thing is, if you are not pushing down properly, then the nickel will not form, and if the nickel doesn't form, it will not make contact with the cell, and then you can eventually result into burning through your nickel strip, and you need to add an additional spot weld on another place. Another thing to be careful about is when you're doing spot welding is make sure that you do the nickel strip and the cell, and not one of them. If you put your electrode only on the cell on one side and the other is still on your nickel strip, you might burn through your cell because the amount of layers between the electrodes is significantly lower. As you saw me just burning through the nickel strip, you would burn through your cell. Now in this case that would be very unfortunate, because you need to take off the nickel strip, you need to remove that cell, replace it with another one, and you can start all over. Now luckily, if that happens to one of those cells, you could cut away one part of the nickel strip, push it out, replace it. But especially when you're working on the other side, and this is already done, it becomes more and more painful. So when you're working with your 18650s, pay attention, take your time, work precise, and if you're feeling rushed, just go watch television or football or something. Don't work with your batteries, because you will make a mistake somewhere which will or can cause damages or other issues. So you need to be in your comfort zone when you're actually doing this. Alright, so that's the second one. I will now shut up and do the rest and speed up the video until this part is done. Alright, all done. Let's make sure that we unplug. Now everything is nice and tight, so we can move on to the construction of the bus bar. So what I'm using is a 6 square millimeter earth cable, which is well, basically thinned. Not sure if that's a correct proper English term, but I'll look it up in the dictionary. So it has a coating on top, which makes it to solder really easy to the nickel strip. Now what I do is I take a measurement, just standard pliers. Let's move you out of the way because you're no longer needed. There we go. Measure it, and I'll always make sure that my bus bar is not protruding the sides of the pack. So let's see if I've done this right. So I cut it, and as you can see, there's like 5 millimeters on each side space, which is more than enough. So the next step that I'm doing is just laying it flat, and I'm going to take a look and make sure that I take out all the kinks out of this wire, so it's as straight as possible before we start the soldering process. And once you're convinced it's all right, and then you're basically good to get started. Well, this one is good enough for me, so I fold over the first and the second tab first. Then I can move the bus bar a little bit, making sure that it is at the right location. The one I'm convinced it's looking good, and I continue with the rest. I fold all the nickel strips over on top of the bus bar, and then once that's done, I take a flathead screwdriver like this one, and I basically push the nickel all the way around the bus bar, making sure that it's really nice and tight around the bus bar. The benefit of it having it very tight is that when you start soldering, the solder will eventually flow underneath. Capillary effect, if I'm saying it right in English, which ensures that the entire nickel strip is soldered onto your bus bar. Now, of course, I'm using also on top the soldering, just in case that if it didn't flow properly, that there's more than enough to make a good contact. So I'm heating up my soldering iron. I put it at a maximum heat, because from here on there's no way that the heat will go all the way through to the top of the cell, into the cell, and then into the inside electrolyte of the cell, making it a potential risk. As I said, cells can't exceed 60 degrees, so you need to make sure that you stay well below that. So we have this one heat up, and then we can finish the bus bar, and that will end also the video for today. And then tomorrow we'll see what the next steps are to get the positive side of the cell pack ready. Now let's see if it's already heated up. Yeah, awesome. So the first joint that you're making, the copper needs to heat up. So leave your soldering iron on the copper for a little longer before you start moving on. And at the end, add the additional solder. Make sure that the entire part is heating up properly. And then the heat will go through the copper bus bar, from one side to another, allowing you to solder much faster than the first one. And if you look very closely when you do your soldering, and you take you put your solder on, you see actually when the solder is flowing under the nickel strip onto the copper bus bar. You see it somewhat like draw in. And then you know for sure that the entire part that you just folded over so nice and tightly is full with solder itself. Now I'll make sure that on my station, as you've now seen how that works, I'll put on the gas extractor, so we don't have all those nasty fumes coming my way, or at least as much as possible. Now, if you're used to soldering, you can see also the difference between the color of the solder when it's actually liquid and when it solidifies. And when you're able to see that, it allows you to make very nice joints and also move forward or make a decision to move backwards in case you see that your solder is not flowing as you hoped it would be. This will take some practice. In the beginning, when I started soldering, I also made a mess, and it really takes at least a couple of months to get this one right, or at least if you practice for a week or maybe 2 weeks, soldering on various components, then you're basically good to go. But in the beginning, probably your solder joints will not look as nice as these, which is absolutely fine as long as they're properly tied into the copper bus bar. So voila. So now let's have a look. So when you're looking close, you can see that the solder actually flowed all the way. And this one is now nice and tight. Done right. So the next step that we're doing is we're making sure that we're going to attach the connection or the interconnect between the cells in the middle, because everything is about resistance. When we're connecting it here at the beginning, I see that done by a lot of people, or at the end, then all the resistance of the copper wire plus all the resistance of the nickel strip will add up. So in this case, we put the copper wire in the middle, so you have half the resistance on either side, and then also the nickel strip is across the cell pack almost the same. This is, I think, a golden rule when you're doing cell pack design. Is make sure that your resistance across the entire cell pack is everywhere the same. And it might be even autistic. Use the same length of wiring, use the same type of connector, use the same type of solder, and repeat that process over and over and over again. Especially if you do a 7S or 14S, you want to make sure that all the resistance of every cell pack in your battery is the same. All right, thank you all. This is a first start. The next episode will be about how to connect the positive side with the cell trace fuses. But that will be a completely separate episode. This one is already, I think, a couple of 45 minutes. So longer than I would have expected. All right, have a great day, and until the next time.